And let's start going over our new material. So this week, we're continuing with some of that background information. Last week, of course, is mostly vocabulary. This week, we want to start looking at organizing data. And most of what we're going to see this week is probably stuff you've seen in one form or another in some of your basic math courses where they had a little bit of a data unit. We're going to look at organizing data graphically. And anytime we look at organizing data, we have to look at the two types of data. Remember, we have that categorical data or qualitative data, where remember, we're answering a question in our experiment, and the answer to that question puts you in a category. Favorite color, what nationality are you? Things like that. What major are you? What degree are you going for in college? Things like that put you into a category. Then, of course, the other is quantitative, or what we refer to as the numerical data. And so there, the answer to the question was a number. How many classes are you taking? How tall are you? How old are you? Things like that were part of that quantitative data. So when we look at organizing data graphically, we do have to break it down by which type we're using. So we're going to start out with qualitative data, because I'm going to guess that most of you have seen most of these displays before. So let's look at an example here. And let's say we're going to try to pick a new school color. Choices are red, blue, or green, sticking to the basics. And we survey a bunch of students, and here's the responses we get. Well, if you look at those responses, if I ask, well, what color is the favorite color or the preferred color, it's really tough to look at that raw data. And that's what this is. It's what we call raw data, and determine what the primary color is. There's just too many of them there. If you were happening to focus over here, you might see a lot of red and think, well, red is the preferred color. But if you were focusing here, you see a lot of blue, your mind might say blue is the preferred color. Whereas if you're looking down here, you see mostly green. So your mind might say green is the favorite color. Human psychological research, and believe it or not, there is actually a very tight link between a lot of the stuff we do in statistics and human psychology. Human psychological research tells us that the human brain can really only view or visualize between 7 and 13 things at once before stuff starts to fade around the edges. So when you're looking at this list of responses, you're really only seeing 7 to 13 of them at once, and the rest of them are kind of blurring. In fact, what your mind actually does is those things that it can't actually observe that are on the outskirts, it fills in values for you. So to bring back my little circle here, if I'm looking here, I see a lot of B's there. Well, these letters out here that my mind is not able to focus on, my mind actually subconsciously fills in B's out there because it expects, because I'm seeing a lot of B's inside the oval here, it expects there to be the same number of B's outside. So my mind actually believes it sees a bunch of B's outside of the oval as well. It's that psychological effect. So it's really, the point of it is, with this size of a set of raw data, it's impossible to just glance at it and get a feel for what is the most common color. So one of the first things we do to organize data is to organize it in a frequency table. And so we're going to start out with a working frequency table. And by working, that means with something we call tallies. Spell it right. And so our frequency table, first for categorical data like this, first we list the category. And that's going to be color. Next would be frequency, but I'm going to actually add an extra column in there. So I'm going to come back to that in just a minute. I'll put my frequency out here. And here, what I'm actually going to add is a column called tally. Now, this tally column is not really part of the graph. but it helps us create the graph. So I'm going to put it in there for now. And then when I'm done, or not part of the table, I should say, when I'm all done, I'm going to make a new table without it in there. So I'm going to list all the values for my variable here. My variable is color, new color. All the possible values, there's red, blue, and green. And now I'm going to go back to my data. I've got red, blue, red, green. Oops, need a different tool to make that work. So red, blue, red, green, red. Red, blue, red, green, red. I'm tallying them into that tally column. Blue, red, red, green, blue. Blue, red, red, green, blue. I'll get through this as quick as I can. I know this is real exciting at this point. Green, red, red, blue, blue. Green, red, red, blue, blue. Red, blue, 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 green. Red, blue, 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 green. Blue, red, blue, green, red. Blue, red, blue, green, red. Blue, blue, green, green, green. Blue, blue, green, green, green. Red, green, blue, green, green, green. Red, green, blue, green, green, green. Red, green, green, blue. Red, green, green, blue. So now I can look at my tallies and I can find my frequency. So red, there were 12 of them. Blue is 14. Oops. And green was also 14. Looking at those original raw data, you probably never would have guessed that it's actually that close to the same. So there's my table. Now, of course, the tally column is not part of my final table. So I would make a new table, a final table, that would look like this. I'm going to leave out that center bar just for speed. So red, 12, blue, 14, and green, also 14. And there's my final frequency table. This is my frequency table for what we would refer to as raw data or raw frequency. Well, since we're on this, it's mentioned raw frequency, let's talk about more that we can do with this frequency table. Sometimes it's not the raw frequency we want. Sometimes we want something called the relative frequency or percent frequency. To create the relative frequency column, what the relative frequency is the proportion of the total. So to find it, we first find the total, and then divide each frequency. So my total here, if I add these all up, 12, 14, and 14 is 50. There's 50 total responses. Actually, not 50, 40. 40 total responses to that, which preferred color do you want to replace the new school color. So to find the relative frequency for red, it's 12 divided by 50, or 0.24. For blue, it's the frequency of 14 divided by 50, or 0.28. And for green, it's also 14 divided by 50, or 0.28. So those are the relative frequencies. And if you remember your basic math of percents, those can be converted to percents rather quickly of 24%, 28%, and 28%. So this should add up to, if we leave it as a relative frequency, of course, it should add up to 1.000. Or if we changed it to a percent frequency, it should add up to 100%. Now, it might be slightly off because this one divided out quite well, but typically if we're dividing by a weird number, maybe 46 or something like that, it's going to be a continuing decimal and we have to round those percents. So it could be 99% or 101%, but it shouldn't be very far off from 100%. Now, I did this one with the frequencies. Oops, go ahead. I heard a question coming up there.
Yeah, sorry to interrupt. I guess the 50 should just be 40, right? Just for the recording.
Oh, thank you. Very good. I should go back and change that. Nice catch.
You're welcome.
I got 50 stuck in my head, and yeah, so that Obviously, it's not adding up to 100 there because I divided by the wrong number. So 12 divided by 40 would be 30 or 0.30. 14 divided by 40 would be 0.35 and 0.35. That should add up a little better. Thank you for catching that for me. So now I purposely did these frequencies close together to demonstrate how hard it is to pick out the most common response from a list of raw data like that. Let's make another table. This one's also, I'm just going to stick with favorite color here. And I'll abbreviate frequency as just FREQ. And we're going to go red, and let's use some numbers that are a little more interesting. So let's put it like this: red, blue, green, 14, 18, 20. Now this is still as a table, and there's only 3 responses, so I can look at this table and fairly quickly tell you which one's most common. But if there were 10 or 12 responses, it might take a while to look through that table and find the most common response. So one thing that we might do to display this to make it a little quicker to pick that data out is to turn it into a graph rather than a table. And one of the more common data displays, graphical displays for qualitative data, is a bar graph. Now, a bar graph can be done one of 2 ways. We can put these categories down the side like this: red, blue, green, and put our bars going, and I'm just going to sketch these in for right now, going like that, going horizontally. Or typically, I mean, that's still a valid bar graph, but it's not the one we tend to use statistically. Statistically, what we tend to use is a vertical bar graph, because our mind, remember we said psychology comes into play. The human mind tends to equate up and down, up with larger, down with smaller. So we tend to take advantage of that when we do our data displays and statistics. So we've got red, blue, and green. And down the left side here, we need to have numbers in a scale so we can get to our largest value. Our largest value here is 20, so we have to be numbered up to at least 20. Now notice I didn't number by ones. I wouldn't have had room. I went by 2s here because so I could make sure I got all the way up to 20. But we can number by 3s, 5s, 50s, 100s, whatever to get up there. So then I draw in my bars for red. It's got to go up to 12, so it's going to look something like that. For blue, got to go up to 18. Now there's a couple of things I'm trying to be really careful to do here. One is I'm trying to make sure these bars are, if not exactly, at least pretty close to the same width. Green needs to go up to 20. And also I'm trying to make sure that there's space, not only space between them, but an equal amount of space between them. Because again, it comes down to that perception in human psychology. If I made one of these bars a lot wider, your brain's gonna say, oh, that's way bigger, even though it might be about the same height. And all that really matters here number-wise is the height of the bar. Another thing I do, the space between them, as I said, keeping that space between them, it's again part of that psychology. Since this is categorical data, there's no logical link or procession from red to blue to green. So we leave the space so that your mind sees that disconnect from one category to the next. Another thing I do is I made sure all of these were done in the same color. A lot of people, especially magazines and the media, like to dress up graphs by having a lot of different colors to them. You may think that's just decorative. It is not. It is actually very intentional because colors are just one of the tools that are used to be deceiving. The color red is perceived as larger by the human brain. They're called hot colors, warm colors, like a bright purple, red, orange. Those colors are seen as larger, where the cool or cold colors are seen as smaller to the human brain, like blue, green, and whatever. So if you have 2 things that are about the same size, if you make one red, your brain's going to think it's larger, perceive it as larger. Now, if you look at these, the blue and the green are, fairly close together, but we can see there's a difference. Now, if I wanted to get the exact number for like blue, hard to say whether that's 18 or 17, but we know it's definitely more than the red and less than the green. If I wanted the exact numbers, that's when we go back to the frequency table. We can get the exact numbers from a table. The graph is best for comparing to find the largest and the smallest, and then comparing what's bigger between two values. Now, something that's often done with a bar graph that can be thought of as deceiving. There's a lot of things that are done as deceiving, but one of the things that's intentionally done that is actually disguised as being trying to help the viewer see the graph might look like this. So I get the bars on here, keeping my spacing between them. What's going on here, though, is because none of them were smaller than 12, we left off those numbers that were smaller than 12, and we just went up above. Now, when you look at this graph, it looks like blue and green are like 5, 6, 7 times larger than red. Well, because there's nothing done here to accentuate the fact that we started at 12, not 0. This graph over here is more honest. It starts at 0 and does the whole scale up. Now, when we do it like this, where we skip numbers and start at something other than 0, it helps us see the difference between them, but it can be deceiving because, again, we're thinking green is like 8 times more than red when it's not. So you have to very clearly mark. Usually they put some sort of a slice or zigzag cut across the graph to bring your attention to the fact that it does not start at 0. Some textbooks will tell you, oh, you can just put like a double hash here on the axis. The problem is if I'm looking at a bar way over here, I don't necessarily see that. There really should be a mark, like I said, a sawtooth cut or whatever, all the way across the graph. So no matter how far you are away from the axis, you're going to see that, and it's going to draw your eye back to the axis. So you see, oh, they're not numbering from 0 here. Again, it's about honesty and working with human psychology to help you accurately interpret the data instead of trying to use your psychology against you. By the way, not to be a little negative, but that the whole field of there's millions, if not billions of dollars spent every year in advertising to do what I just said, use your own human psychology against you, to take accurate numbers or numbers that are accurate enough that you can't be sued for misinformation and presenting them in such a way that fools your brain into interpreting them either in favor of your company or against a competitor, even though the data really doesn't show that difference. A lot of money out there every year for that. And I'm not expecting you guys to go out and make money that way, but one of the things I hope you take out of this course is the ability to look at those graphs and tell, ooh, that is not really an honest depiction. The next display we want to look at is a circle graph or a pie graph, sometimes called a circle chart or a pie chart. And this, of course, does just come off of a circle. And this generally will use the relative frequency rather than the raw frequency. Now, this one is out of 50. So I'm going to do a relative frequency here. Let's see, 12 would be 0.24, 0.36, 0.40. Those are the percents. Now, there was a time when we would convert those relative frequencies into percents and then find what percent that is out of 360, and then take that many degrees and take our protractor and measure it out. Well, right now with technology, we don't need to be that precise by hand. If we want it to be exact, we go to Excel or something and get the exact graph. So for now, we can just use benchmarks. Like we know that 24 is just about 25%. 25% is pretty much a quarter of a circle. So we can mark out just slightly less than a quarter of a circle, and that is the red. And we know 40% is a little less than half a circle. So somewhere in here, that would be the green. And of course, the remainder is the blue. Now I mentioned Excel or electronic means. Let's go ahead and look at that. How would I make these graphs in Excel? Well, I put in my data table. And let's remember the numbers the best I can here. I believe those are correct. So once I put in my data table like that, I just type that in. To make my graph, I'm going to highlight the whole table of data. I'll go up here to insert, and that brings up my charts menu. Now I can either click recommend chart, or I know I want a bar graph. I'm going to go here. Now, this is called a column graph in Excel. A bar graph, Excel calls a bar graph the horizontal ones. The vertical one, what we use as a bar graph, is a column graph. So we'll just pick a standard column graph like that. And there it is. You can see the colors, frequency, you can click and change the title if you want to. And there we have it. If I want to make a circle graph, I highlight my table again and come up here. This one's got circles in it. There's my circle graph. Now it's color coded down here. I could edit this to put the colors in the slices, or to put the actual frequencies in there if I wanted to. All sorts of adjusting we can do. I'll let you play with that on your own. Most time it's a right click on the graph to change any of your adding labels and formatting data series and all that stuff. Anyway, let's talk about quantitative data, numerical data. Quantitative data is a little bit more complex. First of all, let's talk about limited response discrete data. Now remember, discrete data was that countable. How many classes are you taking? How many cars do you own? How many kids do you have? You would count them. It's going to be usually a whole number, 0, 1, 2, 3, 4, 5. Limited response means it doesn't go up to a really high number. You know, we might ask, how many pencils do you have in your backpack? You might have 200 pencils shoved in your backpack. That's a large number. That does not count as limited response. But the number of classes you're taking, that would be limited response. You'd look at, there'd only be, probably up to 4 or 5 classes would be the most you're taking. That would fall into this. So let's take a look at students that have been randomly selected and surveyed for how many classes they are currently enrolled in. And let's say this is our responses, the number of classes you're enrolled in. And so we can see the largest number on there is 5. So I'm going to create a frequency table. With number of classes and frequency. And there's no zeros up there because we're considering it. If you have 0 classes, you're not considered a student at that time. You're taking time off. So the frequency here, look up here, 1. Now I could do the tallies like I did before. These I'm just going to count to go faster. I've got 1, 2, 3. Looks like there's 4 people that are taking 1 class. For 2, I've got 1, 2, 3, 4, 5, 6, 7 that are taking 2 classes. For 3 classes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 that are taking 3 classes. 4 classes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 also that are taking 4 classes, and 5 classes. I've got 1, 2, 3, 4, 5, looks like. I'm not sure what that total comes. Something's a little off on my total there, it looks like, but maybe not. So let's take a look at what this comes up. There's my frequencies. Let's find a total here. Was that 11, 28, 45? That is 50. So that is correct. So I got a total of 50. And I could do relative frequency, Just like I did with the categorical data or the qualitative data, I'm not going to do that here. And of course, we can do all the same graphs. We can do a pie chart or circle graph if we want to. The bar graph would be called a histogram because this is numbers. And so the histogram is going to be exactly like a bar graph, only instead of categories across the bottom, it's going to be numbers. So 1, 2, 3, 4, 5. And we would have the bars in there. Let me number up to. Get up to 20 here. So we got to go at least as high as the smallest number in our data, or the largest number in our data, I should say. And for 1 here, we need 4. So we go up to 4. 2, we have to go up to 7. Now, once again, I am trying to be very careful to keep these bars the same width. And you might notice that the bars are touching. There's no space between them. When we do a histogram, when we do numerical data, the bars will touch because there is a natural flow from 1 to 2 and 2 to 3 and 3 to 4. And they do connect to each other. So the bars touch to psychologically show us that connection and that flow. So their brain looks at it and sees, oh yes, these are numbers. It does transition from one to the next. So we get that. There would be our histogram for this data set. And we could also have what is called a large response discrete. Or continuous data. Large response discrete, like we said, how many pencils do you have in your backpack? Some people might have 1 or 2, others might have a couple hundred. The number of responses could get extremely large. We don't want to list out all those possible single values. Or if I was looking at continuous data, like how long does it take you to complete a certain task? And have several students do the task and see how long it takes them, time them to the nearest 1/10 of a second. Well, again, I don't want to list out every possible time to the 1/10 of a second. So what we do is we create ranges called classes instead of individual values. And we group the data into these classes. So let's look at a manufacturer who wants to see how long it takes its employees to assemble a given part. So we time several employees as to how long it's going to take to assemble that part. Well, this is my data set there. So let's look at the time and the frequency. Now, our time here, let's find our smallest time, looks like with 4.1. And our largest time looks to be about 6.7. So I have to get from 4.1 to 6.7. Now we'll talk about range more next week, but the range here is 6.7 minus 4.1 is about 2.8. And let's say I want 5 classes or 5 groups. So 2.8 divided by 5 would be roughly a 3.5. What am I going to come up with? 0.56, somewhere in there. So let's round it up to just 0.6. So we're going to go from the beginning of one class to the beginning of the next is going to be 0.6. So let's start out with 4.0 is my smallest one. Now we're going to go up to 4.5. Now I said the width is 4.6. Why did I stop at 4.5? Because the next one starts, or the width is 0.6. The next one starts out 0.6 larger. The class width is the distance from the beginning of one class to the beginning of the next, not actually the width of the class itself. So this would go 4.6 to 5.1. This would be 5.2 to 5.7, 5.8 to 6.3, and 6.4 to 6.9. Notice all of those classes are exactly the same size. It's necessary that they're like that so that it doesn't skew the data. If we made them different sizes, we wouldn't be able to compare the frequencies from one to the next. And then we would just go through and count how many fell in each range as we, just like we did with the number of classes taken, we counted them and put in those frequencies. I'm going to assume you guys can put in the frequencies here. I want to move on to another version of our frequency table. And so let's look at, I'm going to look at height and frequency. And we're going to measure students. And let's say we're going to measure them to the nearest 1/10 of an inch. And let's say we got students that go from being 58 inches. And let's go 58 to 62.9. And 63 to 67.9. 68 to, and I really should go 68.0, but 68 to 72.9, and 73 to 77.9. Again, you notice all of these classes are exactly the same size. My frequency, let's say we have in our sample, we had 6 students between 58 and 62.9 inches. Let's say we had 24 between 63 and 67.9, 27 between 68 and 72.9, and let's drop back down to 19. The total here, if I add those all up, was it 30, 57, 76 total. Now there's a thing I can do called cumulative frequency. And cumulative frequency means I want to know what my running total is so far. So when I do cumulative frequency, I actually do need to change my table just a little bit. So I can't just tag this column on at the end. For height, instead of saying 58 to 62.9, I'm just going to say less than or equal to 62.9. And from 63 to 67.9, I'm just going to say less than or equal to 67.9. And then less than or equal to 72.9. And less than or equal to 77.9. So notice I'm just looking at the upper limit of each of the classes. And now when I put in my frequency for cumulative frequency, well, the first one's still going to be the same. It's just 6 because there's only 6 people that were under 62.9 inches. But for this next one, less than or equal to 67.9, well, there's a 24 in that second class, but the 6 are still smaller than that. So I have to add those frequencies together. So the 24 plus 6 gives me a running total or cumulative frequency of 30. Well, the 72.9, well, I've got 27 more that are in that group. But again, all the ones that are in the smaller classes are going with that. So we add those up. Now we're at 57. And then less than 77.9, we had the last 19, gives us 76. This last value here, this last cumulative frequency should always be equal to our total of our frequencies. And so what this does is it allows us to look at this and very quickly say how many people are less than 72.9 inches. Well, that's just 57. And so we can get those running totals or cumulative frequencies rather quickly from there. Rather than just doing graphs like that, there are other ways of summarizing data that are very useful statistically. And one of those displays is called a stem and leaf plot. And in a stem and leaf plot, we have a trunk, which is usually the first digit or sometimes first digits of a number, and then the leaves, which are the next digit. Now the leaves can only be a single digit. The stems or the trunk can be, I'm going to label the trunk stem. The stem or the trunk can be more than one digit in some cases. So let's take a look at test scores. So here's some test scores that we got on a standardized test from a group of students. Looking at this, it looks like we go from 50s up into the 90s. So this is a pretty easy one. So my stems are going to go 5, 6, 7, 8, and 9. The first digit of each number. And then as I go through here, well, I've got a 58. So there are any other 50s? I've got a 50. That looks like the only 50 that I have. I've got a 61, a 64, 67, 66, and a 69. Now I'm not done there. I'm just getting the numbers in the right stem, and I'm going to rearrange those leaves in a little bit. For 70, it looks like I've got 74. Oops, come on back up. 74, 76, 77, 73, 78, 75, 77, 72, 75, 71, 74, 79, 77, 73, and 76. A lot of them in the 70s. For 80, I've got an 84, 88, 81, 83, 83, another 83, 87, 81, 87, 82, 82, 86, and an 84. And in the 90s, I have a 98, 91, 93. I see there's somebody in the chat there. I'll get to you in a second. 91 and a 94. Oops. No, I need to rearrange these. I'll get to your chat once I rearrange these here quick. Now, a lot of people make the mistake of leaving them like this. You don't want to do that. So the 5 should be rearranged, put in order. Well, there's only one of them, so I guess that one's already in order. The 6s then should be put in order. 1, 4, 6, 7, and 9. Make sure you equally space the numbers. The 7s would then be, oh boy, we've got a 1, a 2, a 3, a 3, a 4, another 4, a 5, a 6, and a 6, a 7, a 7, and a 7. An 8, and it looks like a 9 and a 9. Stretch up my windows. That goes back. There we go. For the 8s, I've got a 1, another 1, a 2, a 2, 3 3s, a couple of 4s, no 5s, a 6, a couple of 7s, and an 8. And for the 9s, a 1, a 1, a 3, a 4, and an 8. So now the leaves are put in order. So they're going from left to right, smallest to largest. There are a lot of advantages here. The stem and leaf plot gives us the power of a bar graph for one, because if you look at it closely, you can see this basically looks like bars. That's a bar that's only 1 unit long. This is a bar that's 5 units long. This bar here is, what is that, like 14 units long or 15 units long? 15. Here's a bar that's 13 units long. So just by looking at how long the lines are, how big the string of numbers is, you can actually get a rough frequency for each decade in this case, for each 10, 50s, 60s, 70s, 80s, 90s. So you can very quickly look here and say, well, most of the largest number of scores were in the 70s, smallest number in the 50s. But it preserves the exact number. I can look here and see, oh, there were 3 83s in here, not just that there were 13 numbers in the 80s, but I can actually see the actual numbers within there as well. So the stem and leaf plot is a very powerful plot. Now there's something called a back-to-back stem and leaf plot. Okay, back-to-back stem and leaf plot. We're looking at two sets of data that are comparable. Maybe we're comparing the scores for two classes. And so on this side, I might put class A, the stem, and class B. I should be careful how I space these. There we go. So on the left side, we can see that class A had 2 students who scored in the 60s. Class B had 3. And class A had 4 students who are going to score in the 70s. Class B had 7 students in the 70s, and so on. Now notice the numbers go opposite here. We start at the smallest and go to the largest going this way. On the other side, we start at the smallest and go largest going away. That's the most common way I've seen it displayed, but there are some textbooks and some displays that still go left to right on either side. Most back-to-back plots, they'll start with the smallest numbers in the middle and work their way larger numbers going out. But it's a great way to compare two sets of data, similar sets of data that are evaluating the same value for 2 different samples. Now the stem and leaf plots can get more complex than this. It's possible to have a data set like this. We're looking at the weights of patients. And what this set we're going to look at is going to have large numbers, 3-digit numbers. But you'll note, oops, let's get to the chat here. I almost forgot. Yes, you can only use cumulative frequency with quantitative. You're right. Cumulative frequency would not make sense with qualitative data. That is correct. So here, if I'm going to do a stem and leaf plot, I'm going from 160 up to 230. I can still fit that in the stem by using 2 numbers. So in my stem, I might do 16, 17, 18. That's not spaced out quite so much. 19, 20, 21, 22, 23, 24. That's far enough, I believe. Yeah, 23 would be far enough. And then we could fill in our leaves. So there's a 172, so it'd be a 2 after the 7. 189, so it'd be a 9 after the 8. And we can fill in those leaves like that. So it's possible, if we have a compact enough set of data, to have 2 numbers in the stem. However, let's look at checking account or savings account balances here. This is a set of 3-digit numbers, but they're spread out. You know, these up here, the weights, they were 3-digit numbers, but it was still relatively compact, just going from 160 to 230. We only ended up with like 8 stems there. For this savings account balances, we have to go from 308 up to 833, it looks like, 844. That would be, if we were going 30, 31, 2 digits in the stem, that's going to be 60 stems almost. We don't want that many stems. So what we would do here is, in order to make this work, we're going to put only the first digit in the stem. And then whatever goes in the stem, the next digit in the leaf, the rest is truncated. By truncated, I mean just ignored. I don't say rounded because we don't round up. 487 is not going to go as a 4 and a 9. It's going to be 48. The 7 is just going to be dropped. So here our stem We go from the 300s into the 800s. So it's 3, 4, 5, 6, 7, 8. So this 308 would have a leaf of just 0. The second digit goes in the leaf. The third digit is just forgotten, left off. It's truncated, dropped away. So when we're dealing with stem and leaf plots, you have to be very careful, especially when you're working through ALEKS, to make sure you look and see what it wants for the stem and then make the leaf appropriate. It might say use just the hundreds digit for the stem. That would be what we're doing down here. That means the leaf would be just the tens digit and the ones would be forgotten, dropped off. If it says use the hundreds and tens digits in the stem, that'd be what we're doing up here, where we put 2 digits in the stem and the ones digit is the leaf. So there's a lot of variations of what we can do with those stem and leaf plots. So our final plot, actually there's a couple others, but we're going to switch over to a slightly different type of data. And this is something called a time series set of data. Most of what we've been doing here, we had a single question and we're getting multiple responses all at the same time to that question. For time series data, we're still asking a single question, but we're only retrieving one answer at different points in time. So rather than getting 10 responses all at once, we're going to get one response. We're going to wait a period of time, get a second response from the same thing, from the same element, and then wait another period of time and get another response. An example of this might be cost of gas for your car. If we put our dates down along the bottom, let's go 2010, 2011, 2012, 2013. And we list the dates going along there. Now I realize this could be a potentially sore topic for people if you're paying more for gas than yours, so we're not going to get too into it. But I'm just going to put dots up here. So 2010, let's say here was the price. 2011, it came down a little bit. 2012, back up. 2013, it started to climb. 14, it really climbed. 15, it was up. 2016, it came back down. 2017, it continued to come back down. And we can continue this trend up and down. Then we connect those dots with lines. So this is called suitably a line plot. And the lines, of course, I didn't get my spacing real equal here from one dot to the next. But the line plot shows us a couple of things. Highest and lowest values are usually relatively easy to pick out. The highest value was 2015. The lowest was back in 2010. But then the change is the current change. For example, if I want to look right here, at that point in time, it is increasing and fairly rapidly because it's a fairly steep slope going up. Probably increasing a little bit faster here because that looks slightly steeper. Here, however, it's decreasing because it's sloping down. It was decreasing here as well, but this one is steeper, so it was decreasing faster. So we can see that not only direction of change is it getting larger or smaller, but how quickly it's doing that. That rate of change is also a factor. Okay, so now we are going to get to our final plot of the night. Our final plot of the night is a big tool in finding what's called the data distribution. And that plot is called a dot plot. And so a dot plot is still taking a single question and taking multiple responses to that same question. And it's putting them on a number line. Oops, I see some in the chat again. Categorize the responses for these you don't have to categorize because It's just a single response. So anyway, for the dot plot, let's look at quiz scores. Now, I'm not going to list out the raw data here just for the sake of time, but I am going to make a number line. And that's the first step in a dot plot, is to create a number line that goes from the smallest possible value up to the largest possible value. I don't need this number line to be quite that long, so I'm going to make it way shorter. Let's say the smallest value scored on this quiz is a 4. And it goes up to 10 as being the highest score achieved on this quiz. And so then what we're going to do is we're going to say we score one quiz and it's a 7. So we're going to put a dot above the 7. Score the next quiz and it's a 9. Put a dot above the 9. The next one's a 6. Maybe the next one's another 7. Now there's already a dot there, so we're going to stack them up. Next quiz might be an 8. Next one may be a 10. Next one might be another 8. Maybe another 7. So we stack them up. Maybe a 5, a 6, an 8, a 7, and we keep stacking them like this. And over time, we get a distribution or a shape. You might notice that if I draw a line through this, this looks kind of like a bell curve. This is a big distribution. The bell curve is the official name for it is called the normal curve. Because in nature, that is the shape that most data is normally or regularly distributed in that pattern. And so knowing that a large amount of data is in this shape, what we call normally distributed, then to describe our data next week, when we look at describing it numerically, all we need to be able to do is to find some way to describe where's the center of that bell curve, and then how wide is that bell curve? So these dot plots are kind of the step from what connects the graphical displays, like the dot plot is, to the next step, which is summarizing data numerically by just describing the center and the width or the spread of this bell curve. So that is all of our material for this week. Again, there's other little things that the readings will fill in and the homework will fill in. Does anybody have any questions on what we've covered tonight? Well, I'm sure questions will come up throughout the week. So if they do, send me a message and I'll get back to you as soon as I can. Otherwise, have a great week. And hopefully we'll see you all back here next Monday night.
I do have a question.
Yeah, go for it.
On the bar graphs and the when you were talking about those, as long as the information is going in order from lowest to highest, would you consider all of those types of charts a Pareto chart?
A Pareto chart does not only, usually it's done with categorical data, not numerical data. And yeah, this here actually could qualify as a Pareto chart because it's smallest frequency to highest frequency. So you're absolutely correct. That would qualify as a Pareto chart. A lot of times a Pareto chart, they put a dot in the center of each bar and then put a line in it like that as well, but you don't necessarily have to. But yes, a Pareto chart does do categorical data in order from smallest frequency to largest frequency.
Okay. Thank you.
You bet. Any other questions?
Now you think she's involved.
Okay, well, like I said, if anything comes up, let me know and I'll get back to you as soon as I can. Otherwise, hopefully we'll see you all here next Monday.